So we're going to talk a little bit about rational numbers now. So I just kind of want to put into context where these numbers are. So we have this larger set of numbers called the complex numbers. And you won't really study these until like pre-calculus. Basically, if you've ever heard of imaginary numbers, that's where these complex numbers are. And then if you let the imaginary part of the complex number be 0, then we just have like a nice number that we're used to dealing with, and we call these numbers real numbers. And so that's the subset that we're going to kind of talk about and that you're kind of used to. The real numbers can be separated into two parts. One part is the numbers that are rational. Now, the rational numbers are going to be numbers that can be written as a fraction of integers. You'll notice later on that it's also finite decimals, and repeating decimals are going to be rational numbers. And then the other part of the real numbers is basically all other numbers, and we call those irrational numbers. Some famous irrational numbers would be pi, Euler's number e, or any irreducible root. All right, so let's kind of write a summary for what I just said. We have rational numbers, and that's going to be denoted by this fancy looking Q. That just stands for the set of rational numbers. And we have that some number x is in Q, so this little symbol right here means is in. So x is in the set of rational numbers if x can be expressed as a quotient m over n, where m and n are integers. Okay, and also we have n is not equal to 0, because otherwise when we divide we would get not a number. And then I just want to mention some subsets of the rational numbers, so sets that are also included in rational numbers would be the integers, and those are denoted by this fancy looking z right here. Those are numbers like are -2, -1, 0, 1, we'd keep going 2, and on and on and on either side. The whole numbers, which are basically the positive integers and 0. And the natural numbers, which is denoted by this fancy looking n, and those are all positive integers, not including 0. Okay, so suppose we wanted to categorize the following numbers. So if I'm looking at 5, this would be for sure an integer. It's also a whole number. It's a natural number. And it's rational, specifically because it can be written as 5 over 1, so a ratio of integers, and 1 is not 0. Now when we look at 1.23, that's not an integer or a whole number or natural, so we're left just trying to decide whether it's a rational number or an irrational number. And so we're left with the decision of, can this number be written as a ratio of integers? And for this one, the answer is yes. Notice that if I move the decimal place over 2, then I get 123. And the reason why I'm pointing it out that you move it over 2 is because if I take 123 and I divide out by 100, that's equivalent to moving that decimal point over 2 this way. So I've got 1.23, and so I've expressed this number as a ratio of integers, 123 over 100, and so that means that this number is rational. I can play a similar game with this next number, -4.83295, by noticing, hey, if I move this decimal point over 1, 2, 3, 4, 5 places, then I'm staring at an integer. And so I can write this as -4.83295 divided by a 1 followed by 5 zeros. and these two numbers are equal, and I've expressed that number as a ratio of integers, and so that means it's rational. Okay, and so I want you to notice the trend right here is that if I have a finite decimal, and what I mean by finite is I only have like a certain number of digits after the decimal place. After that, it terminates, or, you know, I can fill in just like zeros. So finite decimals, those are going to be rational, because I'm always going to be able to play that game where I divide by a 1 followed by however many zeros as you have digits after the decimal place. Okay, next we have this number 0.3 repeating. Now remember, this bar over the 3 means that I have 0.3 and it repeats. So I have 3, 3, 3, on and on and on. And it never stops. I have infinitely many 3s after the decimal point. Well, you might recognize this number. You probably see it a lot in your calculator, because this is identically 1/3, which is a ratio of integers, which means that even though 0.3 repeating repeats forever and ever and ever, we can still express it as a ratio of integers, which means that it's a rational number. All right, so now I have 0.25 repeating. And this one you probably haven't seen very frequently, or maybe even at all. But I'm going to show you kind of a trend that we have with repeating decimals. And it's that if I take the digits that are repeating, so 2, 5, and I divide it by the same number of 9s as I have digits repeating, so I have 2 digits that keep repeating, so I'm going to divide by 99, you'll actually get this repeating decimal. And we can see this trend when we do this division as a long division. And I want you to notice the trend that when we have a repeating decimal, we end up getting that it is rational. And we're going to use this trick with the 9s every time in some way, shape, or form. And then I have at the bottom here 2 kind of famous irrational numbers. These both happen to be infinitely long, non-repeating decimals, and for now you just need to know that if a number is an infinitely long non-repeating decimal, then it is going to be an irrational number. And we will not be able to write it as a ratio of 2 integers. All right, we have 2 more problems. So the first one is to prove that 1.2 repeating is rational. So I put this one in here because we can't just right away stick it over a 9. If you try to do 12 divided by 9, you're not going to get 1.2 repeating. So instead we're going to break this up into, so we have 1.2 repeating. We're going to break this up into numbers that we know how to deal with. I know how to deal with 1, and in fact I know that that's a rational number. And I'm going to add it to 0.2 repeating. Well, 0.2 repeating I can write as 2 over 9. And then I can add these together and get 9 over 9 plus 2 over 9, which is going to be equal to 11 over 9. And if you type 11 divided by 9 into your calculator, you will in fact get 1.2 repeating. And I want to make a note right now. If we add 2 rational numbers, that will give us another rational number. And it is because we can play this this game where we separate into rational numbers. And if we have a sum of fractions of integers, then I can just get all of them with a common denominator, add them all up, and then I'll have another fraction of integers down here. All right, now we're going to prove that negative 1.03 repeating is rational. We could go back to this, we can break it up and add two rational numbers together, and that gives us a rational number. That's perfectly fine from this point forward, but I want to go ahead and show you for this one how you could kind of deal with it, because I think that it will help you understand kind of how these numbers are working together. All right, so I'm going to write negative 1.03 repeating as negative 1 minus 0.3 repeating. Whoops, hold on. Minus 0.03 repeating. And now I'm going to try to deal with this. Well, if I had 0.3 repeating, I could just write 3 over 9, which is 1/3. But I don't have that. I have 0.03 repeating. So I need to deal with this 0. And the way that I can do that is by writing 0.3 repeating, which I know how to deal with, over 10, because that's going to move my decimal point. So now I have negative 1 minus 1 over 10 times 0.3 repeating, which I know is 1/3. Well, now I can just combine everything at this point. I have negative 1 minus 1 over 30, which is equal to 30, or negative 30 over 30 minus 1 over 30 gives me a negative 31 over 30. And if you type that into your calculator, you will in fact get negative 1.03 repeating.